Right, welcome a Chaks solution matrix systems of linear equations. Right, so a system of linear equation, these are equations that have these are two or more equations that have variables where we need to solve for those variables. Right, so we can solve the systems of linear equation using the inverse. So if you look at this one, we have three equations that we have where we need to solve for x, y, and z, and other values are constants here. Right, so these systems of linear equation can be written in matrix form. Right, so we write a, b, c, d, e, f, g, h, I here. So you can see a is the coefficient of x, and b is the coefficient of y, c is the coefficient of z. So we do the same a, b, c. Then on d, e, and f we do also the same, and g, h, I do the same here. Then we are times the matrix x, y, z is equals to kp n here. Right, so now we can find x, y, z here by multiplying with the matrix, the inverse of this matrix here. So let's assume that this matrix is A, so it's going to be A times XYZ is equals to this matrix. So now we can multiply in the first position of this matrix A inverse times A, such that we can have the identity matrix here. Then XYZ equals to A inverse times KPN here. So we are multiplying in the first position. So in this side we also multiply in the first position here. Alright, so A inverse times A is the identity matrix. So we'll be left with X, Y, Z here equals to A inverse, then KP N here. Alright, so the systems of linear equation are said to be consistent if we have one solution which satisfies the all three equations. So if we solve these equations and we produce a solution, so if that solution is satisfying the first equation, second equation, and the third equation, it means the equations are consistent. So they are meeting. Consistent, we are just saying they are meeting at that specific point. Right, so let's go to our example here. Solve the systems of linear equation below. Right, so these are the three equations that we have. So the first thing here is to write our equation in the matrix form. Right, so it's 1 minus 4 2 1 1 1, then 2 1 minus 3 xyz is equals to minus 2 6 0 here. So then we can say let A equals to this matrix that we need to find the inverse and multiply both sides here. Right, so A times xyz is equals to minus 2 6 0 here. So now we need to multiply both sides with the inverse here of A in the first position. So A inverse times A is equals to A inverse times minus 2 6 0 here. So now xyz is equals to 1 over minus 26 minus 4 minus 10 minus 6 5 minus 7 1 minus 1 minus 9 5 times minus 2 6 0 here. So this one is the inverse of A here. So if you haven't watched videos on inverse or finding the inverse, I will encourage you to go and look for those videos on our lesson on inverse of a 3 by 3 matrix. This will be very helpful. So this is our inverse here. Right, then you multiply row by column. So you first multiply with this matrix on this one, then later on multiply with this constant 1 over minus 26 here. Right, so this is x is equals to 2 and y equals to 2 and z is equals to 2 here. So this is the solution here. Right, so let's go to the next example. Right, so on the next example, given that A is equals to this matrix and B equals to this matrix, find AB, hence or otherwise find A inverse, then hence or otherwise solve the systems of linear equations here. So we are going to start with item 1 here. So we are multiplying A times B here. Right, so A times B. Right, so this is our item 1, A times B, a multiplication of matrices, a row by column. So if we multiply A and B, we are going to have this matrix which is minus 8 minus 8 minus 8. So we have minus 8 on the leading diagonal. So automatically now we know that A and B are related in such a way that A is the matrix and B is the adjoint of the matrix A here. because we said if you multiply A times B, we'll get the determinant on the leading diagonal here, and the other element will be the zeros. And yeah, so in this case, this is our matrix this is our situation that we have here. So A is the matrix and B is the adjoint of A here. All right, so now they are saying hence find the inverse. So inverse of A is now very simple, because we see that the determinant is minus 8 and the adjoint of A is what? Is B. But remember that also the adjoint of B will be also A here. So that's the same situation. All right, so let's go here. You can see A times adjoint is equals to det of A on the leading diagonal and the zeros that we have in the on the remaining elements, right? So the inverse of A is now simple, so it's 1 over minus 8 times the adjoint here. So the adjoint is the matrix that multiplies A and produce this a matrix with the leading diagonal, which consists of the determinant here. So the inverse is now this one. All right, so it's very simple. The otherwise part is to maybe go on those processes where you find the matrix of minors. After finding the matrix of minor, you go for matrix of factors. After finding the matrix of cofactors, you find the adjoint and you transpose. Then you write your inverse. Yeah, this is the otherwise part. But the hence part here, we're just looking at the situation where we are saying A times the adjoint of A is equals to det on the leading diagonal, and the other element becomes the zeros, right? So now let's go to the hence part here, where they're saying hence or otherwise solve the systems of linear equation, right? So this system of linear equation can be expressed in matrix form. So we just write the coefficients of x, y, z following their order here. In the first row we write 3, 2, minus 1. Second row minus 4, minus 8, 4. Third row minus 1, 2, 3 here. Then x, y, z. Then we write the resultant answers here on the right hand side, right? So now we need to multiply both sides with the inverse of this matrix here. So I just assign that matrix to be A. So we have A, x, y, z. Then A inverse in the first position, A inverse times A, so that we have the identity matrix here, and we're left with x, y, z is equals to A inverse. So we are multiplying the first position here. All right, so now x, y, z is equals to 1 over minus 8 times this one, which is the inverse of A, times 2, 0, 1. So this will give us 1, 0, 1 here. So you can now see x is equals to 1, y is equals to 1, and z is equals to 1. So these are the solution for these systems of linear equation that we have here. All right, so let's go to the next example. All right, so our next example, given that A is equals to this matrix, and the first item is say find the inverse of A, hence or otherwise solve the systems of linear equation here, right? So we need to find the inverse of A and we solve these systems of linear equation. All right, so it's very simple. All right, so to find the inverse, first we find the determinant of this matrix. So determinant, we said you can expand the first row here. So finding the determinant by expansion of the first row. All right, so it's very simple. So it's close the row of 1 and the column of 1 here. Then we are left with this one. Then you go to minus, then minus 1. You close the row of 1 and column of 1. Then we are left with this minor here. Then plus 0. You close the row of 0 and column of 0 here. Then we are left with this minor. Then we simplify. Then we are having minus 3 as our determinant. So if you haven't watched the videos on finding the inverse of a 3 by 3 matrix, I would encourage you to go and look for the video, watch those videos, make sure you understand those concepts, because we are building on those concepts. Right, so this is the determinant here. All right, so now we want to find the matrix of cofactors. So matrix of cofactors, we need to find the cofactor of matrix of cofactor here. So the first thing is to find the matrix of minus here. So this is the minor of 1, this is the minor of minus 1, this is the minor of 0, this is the minor of 5, This is the minor of -4, this is the minor of 1, this is the minor of 2, this is the minor of 2 here, and this is the minor of 1. Then to have the matrix of cofactor, we multiply with the corresponding sign here, which is plus, minus, plus, minus, plus, minus, plus, minus, plus here. Then we have this matrix of cofactors. So now to find the adjoint here, we can transpose the matrix of cofactors so that we have the adjoint. So at the adjoint here is the transpose of the matrix of cofactors. Then we have this matrix here. So now we can write the inverse here. So the inverse is now very simple. So inverse is equals to 1 over the determinant times the adjoint, right? So this is our inverse here. All right, so now we go to the hence part here. So the hence part, it means we are using the results that we have here to find the values of x, y, and z here, right? So now is to express our systems of linear equation in a matrix form, right? So we express in matrix form here, right? Then we just let this one to be a, then a, we are going to multiply both sides with the inverse of a, then we multiply with the inverse of a both sides. So a times inverse is the identity matrix. Then x, y, z is equals to a inverse times -4 minus square of 11 here, which is the result on the other side. All right, so x, y, z is equals to inverse of a times -4 minus 12 11 here. So you multiply row by column, so you multiply this matrix with this one, and later on multiply with this constant. It will be easy here. Then we have x is equals to -1 over 3, and y equals to 11 over 3, and z is equals to 13 over 3 here. So this is the values of x, y, and z here. All right, so let's go to the next example. All right, so our next example, we are saying given that a is equals to this matrix and b equals to this matrix, find ab, that's the first part. And item 2, given that ab is equals to this matrix with the determinants, which is on the leading diagonals here, right? We are required to find the value of k. Then it is also given that ab times xyz is equals to 3, 1, 2 here. Find the value of xyz here. All right, so multiplying of a times b, so a times b is row by column. We are going to get this matrix 3, 5, 1, 2, 0, 3, 4, 2, 4 here. So this is a times b. All right, then we are given that ab, which is this matrix that we get, times this one. This matrix must have this one. So this is item 2. So this is our ab. So we're going to take our ab and multiply on this part and see the value of k here. All right, so this is our ab times this one. Then we get 6 on the leading diagonal here. So what does it actually means here? It means that ab is a matrix here. Its adjoint is this matrix, and the determinant is 6 here. All right, so now let's go to the third part here. So the value of k here is 6 here. So item 3, now we need to find the value of xyz here. All right, so xyz, so ab times xyz is equals to 3, 1, 2 here. So now we can multiply both sides with ab close brackets inverse times ab, because ab, remember, it's a single matrix. So that single matrix here, it's ab inverse times ab. xyz is equals to ab inverse times 3, 1, 2 here. Right, so in this part we are going to have the identity matrix. Then xyz is equals to the inverse times 3, 1, 2 here. So you multiply this matrix times 3, 1, 2. This will give you -1, 1, 1 here. Then automatically we can now see the values of x is equals to -1. Then the values of y equals to 1, and the value of z is equals to 1 here. Right, so this is the problems that we have in this lesson. Thank you for watching the video. See you in the next lesson. Right.